Okay, so welcome everyone again to today's edition of the research seminar. Today's presenter is actually Balázs Madas, who will be talking on microdosimetry as a natural link between experimental and observational research. So Balázs is a senior research fellow at the Environmental Physics Department at the Hungarian Research Network Center for Energy Research in Budapest, Hungary. He has obtained his PhD in physics. Modeling biological systems is his main research field, where he mostly focuses on the biological response to ionizing radiation. In his models, there is almost always a link between death and variability, nowadays between cell death and mutagenesis. He has been studying the biological effects of inhaled radon progeny for a while, learning a lot about internal alpha dosimetry and a little about aerosol transport. So with that, Balázs, I would like to hand it over to you, and we're looking forward to your presentation.
Thank you very much, and thank you very much for your nice introduction. First, I would like to add some kind of disclaimers to the title. The first one is related to microdosimetry. You can find many different definitions for that, and I use this term or define this term as everything which is covered in a series of microdosimetry conferences, which was held every 4 years for many decades in Italy. The main point is that it's not just dosimetry, it's also considers modeling of the biological response which are related to doses to individual cells. And the other point is that the presentation rather focuses on the need of microdosimetry and not really solves every problem, because it is not solved, but I would like to show just that these are very important if you want to understand the effects of ionizing radiation, and in particular ionizing radiation from inhaled radon exposure, inhaled radon progeny. I cannot. So first, what will we cover? What are the fundamental questions of radiation protection research, or at least 2 of them? Then we see where do we get answers from to those questions. An important point that where does things happen? That will be the main point of the presentation. We will overview heterogeneity at many different spatial scales, and we will distinguish between 2 main reasons of heterogeneity, which are very important to keep them distinguished in our minds. So fundamental questions of radiation protections are: what are the harmful effects of ionizing radiation? Because these harmful effects generates the need for protection. And another important point, how do they depend on the exposure, or I can say on the dose? And within this radon project, we are particularly interested in the stochastic health effects of ionizing radiation, in the carcinogenic effect of radiation, and in lung cancer induction by radon exposure. What are the sources of our knowledge? So how can we get more information on the effects of ionizing radiation and their dose dependence? There are 2 major kind of research. One are the epidemiological studies, where we observe how disease, morbidity or mortality from a disease are related to the exposure. There are 2 major disadvantages, that there are confounding factors and co-exposures which cannot be controlled, because they are we just observe what we see in among people who are exposed in uncontrolled situation. And there is a clear limitation in case of low dose exposures, because if we go down with the dose, then the risk will be also smaller. And if we have a small risk, then we need a large population to observe any effect. However, what is the major point that epidemiological studies are our only source to get quantitative information about risk of radiation on human health. The other important source of our knowledge are coming from experimental studies, where we have a controlled environment, so we can fix other parts and focus on the effects of ionizing radiation. It is very important that we can follow what is happening in the experiment, so it provides information about the mechanism, how the effects propagate. But the difficulty is, or the disadvantage, that we don't get quantitative information on human health effects. There are in vitro studies where we focus on cells or tissues, but in that case, it's not a risk of human health. Or if we use animals for our studies, then we can see health effects like cancer, but it is not straightforward how we interpret these data on how we translate these data to human health risk. And the question whether there is a way how we can use both group of the advantages of the two kind of studies. So how we can use what we learned from experimental studies on the mechanism performed in controlled environment, and whether we can link them to quantitative information about risk on human health. And the first question, whether there is a link at all. But what can be a promising fact that if you look at the levels, different levels of biological organization, we can see that there is a hierarchy in the living organism. So what are observed in epidemiology, these are practically populations, and what we do in our experiments, that we look at the effects of ionizing radiation on cells, in some cases tissues, and considering that our body, we as organisms are built up by cells and tissues, and we form populations, we can hope that there is a link between the observations made by epidemiology in the population. We are particularly interested in the effects on tissues and organs, because what we are interested is lung cancer risk, and lung is something like an organ, somewhere above the organs but below the organ systems. So what we want to observe, what we want to know is cancer risk. So if we understand how cancer develops, then it definitely helps our understanding for dose-effect relationship. But if we consider that we also know, we can also distinguish between different histological types of lung cancer, we can see that we can say that it's practically the disease of the tissue. So if we understand how the tissue changes, what are the effects of ionizing radiation in the tissues, in particular radon exposure, then we get closer we can get closer to the dose-effect relationship. So the next question, whether if we are interested in the tissue and organ level effect, how they depend on the effect of molecular and cellular level effects. Again, the question whether there is a link at all, but it will be really much needed, because what we can most frequently observe or most frequent experiments are done at these levels on what is happening at the cells upon exposure to ionizing radiation. So the question whether we can be sure that these levels are important. And for that, I would like to show an example which shows the importance of the levels below the tissue level. And for that, I would like that you consider how much is 4 gray absorbed dose in the human body. And probably most of you know that it's a quite high dose. It is also called semi-lethal dose, which doesn't mean that people become half dead upon exposed to 4 gray, but it means that if 100 people are exposed to this dose and don't get medical help, then half of the people will be die. So from that perspective, it is quite a large quantity. However, if we consider how much energy is this dose, how much energy is needed to be absorbed to get this dose, then we have to consider a mass of the human body, let it be 70 kilograms, and then we get that it is 280 joules. And if we find other examples in physics, how much is 280 joules, then we find that it is a rather small quantity. So in terms of potential energy, which means an increase, which changes, for example, if someone is lifted, then 40 centimeter. So if I step up to the chair, it's equivalent to this amount of energy. Would be equivalent if it would be just 70 kilogram, which is not the case. So it's very little. If it doesn't make a big effect if I fall down from 40 centimeters. It's just if I run to the tram and run down on some staircase. I'm not sure that's the word. So anyway, it is an everyday experience. And if we search for another example, then we can see that, for example, a single sip of coffee or tea also results in that much heat energy, which is again another everyday experience for us. And I don't have to talk much about it. It's absolutely not dangerous for us. So these are everyday experiences. So there is a major difference between the effect of the same energy from ionizing radiation and from other sources like heat. And the question, what are the difference behind what is the difference in the energy deposition of ionizing radiation, coffee, and lifting? And the key word is that ionizing radiation is capable of ionization. So that's the main point. So there are tiny energy packages from ionizing radiation which are able to break chemical bonds, and that is the reason that we have strong biological consequences, much, much, much stronger than if this energy is provided by heat or something like that. And these are the initial events. So if you look at the effect propagation upon radiation exposure, then we see that they start with these ionization events, which are physical processes. Then there is a physicochemical and chemical stage of the effects, which takes longer, but they are still very, very quick. And we reach our everyday time scale with DNA repair, cell death, and such biological effects. But it is important to note that if we are interested in, for example, in lung cancer death, then we are on a very different time scale. And again, at this point, it's important to note that what can be observed in epidemiology, morbidity, and mortality data, these are on very different timescales. And even if we know that there is a linear relationship between radon exposure and lung cancer risk, we have the problem with low exposures, low exposure rates, because in that case, we have to extrapolate, or maybe we can say interpolate from high exposure data. But such kind of extrapolation can always be a bit dangerous to show it. I frequently tell a joke, which probably you already know. So if there is a flight which travels between London and New York, and it has 4 engines, and the duration of flight is about 6 hours, then we can imagine the situation that after takeoff, the captain tells that unfortunately one engine went wrong, so we have 3 engines, which means that our travel will take 8 hours instead of 6. And a couple of minutes later, they talk again that another engine went wrong, and therefore the travel will take 12 hours, and then goes on. After the 3rd engine goes wrong, then it's 24 hours. And when the captain talks again and said that the final engine went also wrong, then some of the passengers says that, oh, we will be in the sky forever. And that's a reasonable conclusion based on the extrapolation of the times and the working engines. But if we understand how an airplane operates, then we know that that's not the outcome. And this is an example that if you want to extrapolate, if you want to use some kind of mathematical models and estimate cancer risk at low doses, or in case of low exposure rates, then it's important that we understand the mechanism. And if you want to understand the mechanism, then it's a crucial point that the biological response can only work on what physics left behind. So physical processes are the first which happen upon ionizing radiation exposure. So biology is much slower, proteins are much slower, and therefore it is crucial to understand what is the physics behind an ionizing radiation exposure. And if we have any new observation in radiation biology or radiation epidemiology, the first thing we have to consider whether there is a physical explanation. Of course, it doesn't mean that we always have physical explanation. Of course, physics doesn't explain everything, but it's important that we understand, for example, whether there are differences between the type of exposures. And so if the doses are different in case of different scenarios, then there is no reason to expect the same consequence. So what we have seen that the energy deposition at the nanometer scale is crucial in the effectiveness of ionizing radiation. And based on that, we can expect that other scales, spatial distribution of energy deposition, other scales can be also very important. And here there are 3 examples. So if we see differences in energy deposition within the cells on a micrometer scale, within tissues and organs, a centimeter scale, or within the organisms, we can expect differences, and we will see that these differences are also, some of these differences are also considered by radiation protection, as we will see. So the first difference, that different types of ionizing radiation has different effectiveness, causing biological effects. In this picture, you can see some kind of DNA repair proteins in a cell nucleus, and you see that in case of charged particle, in case of ions, these DNA damages are along a line. So it is a very different distribution of energy deposition events compared to X-rays or gamma photons. And they are much more effective in causing cell death and many other biological outcomes. And therefore, we also apply radiation protection, radiation weighting factors, considering this difference in energy deposition events, the distribution of energy deposition within the cells. There is another aspect, there is another major difference between charged particles and X-rays, and it is related to hit statistics. So on the left side, you can see to absorb those values in tissue. On the left side, they come from X-rays. On the right side, they come from alpha particles. The values are just showing the orders of magnitude, not exact numbers, but you see that the same dose from X-rays and from alpha particles results in very different distribution of energy deposition event, very different hit distribution. Hit means if alpha particle hits a cell, or in case of X-rays, if the X-ray electrons generated by X-rays hit a cell. And in case of half gray, which is quite high value, is of X-rays, that mean the mean number of tracks per cell is around 500, which is quite high. So if the probability distribution is the same, so all the cells have the same chance to be hit by an electron, then it means that what we see is a rather homogeneous distribution. In case of half gray from alpha particles, the mean number of tracks per cell, the mean number of hits per cell is only around 1, which, considering the Poisson statistics, means that around 37% of the cells are not hit at all, and the cell dose or specific energy is 0 gray. 37% of the cells are hit by 1 track, and it results around half a gray in those cells, and the rest of the cells are hit by more than 1 track. So the same dose results in a homogeneous hit distribution in case of X-rays, but a heterogeneous hit distribution in case of alpha particles. If we go down to 1 milligray, then we see a similar hit distribution in case of X-rays, what we have seen in case of alpha particles for half a gray. So in that case, we already see an inhomogeneous hit distribution also in case of X-rays. However, now the dose is, of course, much lower. And if we consider a low dose in case of alpha particles, 1 milligray, then the mean number of tracks per cell is around 0.02, which means that 99.8% of the cells are not hit at all, but a small fraction, 0.2% of the cells are hit by one track and receive quite a high dose. So that is an important difference between charged particles, alpha particles, and X-rays, which we have to consider. However, this is not just the only source of heterogeneity in case of alpha particles, because what we have to consider that although we see differences, so some cells are hit while other cells are not hit, the hit probability is the same for all cells. We can also formulate it another way. So as we see on the left side, if we increase the dose, the hit distribution becomes homogeneous. If we would increase the dose for alpha particles too, so we would multiply the dose by 500, which means a very large number, 2.5, 2.5 kilograms. Of course, that's an extremely high number. But in that case, we would see a homogeneous hit distribution, even in case of alpha particles. So this kind of heterogeneity, in case of alpha particles, comes from the low hit number, comes from the fact that the dose from a single alpha particle is very high. So if the average dose is not high enough, let's say 2.5 kilograms, then the hit distribution will be heterogeneous, even if the hit probabilities are the same. Sometimes it's difficult to find a good analogy for that, but what can be a good example that if we look at the ground when it starts raining, then we first start to see some dark spots where the rain drops fallen. So at the beginning there is a pattern. So not all the ground became dark, we just see the dark spots. And this is what we see in case of low dose alpha particle exposures. The difference, the inhomogeneity, the pattern come from the low number of alpha particles. However, it is also possible that the hit probabilities are not the same, and in that case, the hit distribution will be even more heterogeneous. For example, it's similar if there is rain, we have the same kind of rain, but we are under a large tree. So in that case, the source of the heterogeneity, not just the low number of alpha particles, the reason of the pattern on the ground is not just that it's just started raining, it's because there is a tree which covers part of the ground and we see a different pattern. And it's very important to consider, if we perform experiments with alpha particles, that it is a possibility that the inhomogeneity not just coming from the low number of hits, but also from the fact that we couldn't expose our cells in a homogeneous way. And that can be also important in radiation protection. So you don't expect the same effects if 500 milligray is absorbed homogeneously in an organ or absorbed in a single cell of the same organ. That was just general, and what I would like to point now that all scales are highly relevant in case of radon exposure. So we see on the right side a sketch of the bronchial epithelium, or not just the bronchial, but also epithelium in deeper airway generations. And of course, it is important that these cells are exposed to alpha particles. So we can imagine that even if the hit probability will be the same for the same type of cells all over the lungs, then some of them will be hit and some others wouldn't be hit. If these alpha tracks deposit the energy along the line, it not only affects the hit distribution, but also the energy deposition along the line are not homogeneous. And that is just one aspect. So radon progeny results in alpha particles, and therefore there is some cells will be hit and some others are not hit. We can expect a difference because what we see different types of ionizing radiation are differently effective, has different effectiveness, and so radiation rating factors are applied also for radon exposure. But the other point is that in case of the lungs, we have a heterogeneous deposition of radon progeny. So it works as a filter, our lungs. So particles, only those particles can deposit in the deeper airway generations, which didn't deposit in upper airway generations. So there is a difference between the dose in the different bronchi or different bronchioles. And in addition, we also see a difference in the deposition distribution within a single organ or a single airway bifurcation. And it remains a question whether it affects the effectiveness and whether it should be introduced some kind of weighting factor or not. And of course, which is not seen on this figure, but radon progeny are also transferred to other organs, and therefore risk of cancers other than lung cancer can also be increased due to radon exposure, as it is also studied in the task other work package of radon. So, and how we have to make these links between the experimental studies and the in vivo level and the in vitro level. So one important goal of our work in radon was to quantify the dose distribution within the human lungs to plan in vitro experiments. So while the exposure can be described by the radon concentration in the room around us, it's not so straightforward that determine to what kind of doses our cells are exposed, especially considering these deposition hotspots, which can be seen at the peak of the bifurcations. So one relevant question, what are the effects of locally high doses? And these are also studied in radon. Besides the planning of these in vitro experiments, so what are the relevant doses which are mimicking the in vivo situation, it was also an important goal that we help to evaluate and interpret the results. So if there is an in vitro experiment with some kind of alpha source, then what should be the distance, what should be the exposition time to result in a similar dose as we expect in case of the human lungs. And of course, we also have to consider here that even in such an experiment, we can have a different dose distribution, not only because of the high energy and small number of alpha particles, but also because of the geometry. So for example, in the middle of such a cell culture, you can see much higher doses. And if we apply some kind of shielding, then of course there will be a sharper decrease in the dose distribution. So the main point which I wanted to highlight, that it is very important to understand where things happen in case of ionizing radiation exposure, and in case of radon exposure, many different special skills has to be considered because these are alpha emitting radionuclides and they deposit very heterogeneously in the lungs and very heterogeneously in a single organ of the lungs. So that's from my side, and I would like to thank Árpád Farkas, Gábor Albrecht, and Péter Füri, who were working on the determination of dose distribution in vivo and in vitro environments.